Welcome guys, Mr. Apanah here. Welcome to the next lecture. Today we're looking at the life of a star. What I'd like you to be able to do by the end of today is be able to explain some of the ways that stars can be different. We know when we look up to the night sky that some stars seem brighter than others, and we want to know why that actually happens. And I also want you to describe, why do stars actually burn brightly? How do they burn brightly, and what is going on inside the star? So, stars do burn bright, we know that, and we already know that stars are mostly hydrogen with a big chunk of helium, plus there are some larger elements like iron as well, though they're very little of these larger elements. Now there's massive temperatures inside the star, huge temperatures, millions of degrees Kelvin, okay, and that word is Kelvin, which is a different unit of temperature. We're used to degrees Celsius, but degrees Kelvin is what scientists use when they're studying temperature. And these massive temperatures, what happens is that the normal atom doesn't actually stay as we would normally see on Earth. So we're used to having an atom which has a nucleus, and then it has a shell or an orbital, and you would find an electron in that shell and a proton and neutron in the nucleus. So that's hydrogen there, one proton, one electron. Hydrogen. And what happens is, because the temperatures are so high, this electron can't actually stay bound to this proton. So it turns into a soup of protons and electrons. And this is actually what we call plasma. Okay, plasma is the fourth state of matter after solids, liquids and gases. So we're used to solids, liquids and gases on Earth. Inside the Sun, they also have the fourth state of matter, which is called plasma. Inside the Sun, we know that nuclear fusion occurs. We know that fusion means to come together, which is the opposite of fission. Sorry, you just have to excuse my writing. It's a bit tough. Fission means to break apart. Fusion means to join together. This is what happens on Earth, okay, in our nuclear power plants. And we take a large atom, such as uranium or plutonium, and we allow that atom to break down and to split. And when it splits, it releases energy. Now, the bad side of that is that it produces nuclear waste. At the moment, we don't know what to do with that nuclear waste. Nuclear fusion, on the other hand, is what occurs in the stars and is kind of what we're looking at here on Earth. And what the good thing about nuclear fusion is that the only product of nuclear fusion is helium. And helium is something that's actually in short supply. So it actually would kill two birds with one stone if we could harness nuclear fusion. The problem is that it happens again under this enormous temperature and enormous pressure, much more than what we normally see here on Earth. So in order to create these pressures and temperatures, it takes a lot of energy, which is why nuclear fusion is very tough to see on Earth, but occurs en masse in the stars. So what is nuclear fusion? Basically what you do is you get the nuclei of atoms, which are the protons, and you bounce them together at high speed, and what happens is they create this thing here. This is deuterium. Okay, this deuterium is like a hydrogen in the fact that it's got a proton. And what you do is you get this deuterium and you react it with more protons and you create helium. And what we've done is we've basically added things together, and this adding of things together is called fusion. So this is what nuclear fusion is. You take something small, like protons, which are remember they're in the soup of the Sun, and then you add them together under this enormous pressure and temperature, and eventually what you get is helium. Okay. These things over here, this positron and neutrino, they are something a little bit different. Basically, they come about because when these two protons add together, you notice that one of the protons loses its charge, and that's its charge over here. It's called a positron. So let's have a look at stars themselves. Why are stars different? Well, stars can be different because of their mass. Okay? Now, their mass is basically the amount of hydrogen which is in them. Okay, because remember, hydrogen is the most abundant element in the star. So the more hydrogen, the larger the mass of the star. The less hydrogen, the lower the mass of the star. They can also be different brightnesses. Now, this you should be able to see when you look up to the stars, and you see that some are a little bit brighter, some are a little bit duller. So the apparent versus the absolute basically means Apparent is when you are looking at the star from Earth. The absolute is the actual star itself and how bright it is. We can also look at the temperature of stars, okay? You can measure the temperature of stars, and that also leans to the colour of the star. The brighter the star, okay, we look at this sequence down here. The brighter the star, this is the luminosity or brightness. So the brighter the star, the more blue it is. The duller the star, or the cooler the star, the more red it is. Now, you might think that sounds a little bit weird, but think about our Bunsen burners, okay? If you've got the safety flame on, which is the yellowy, reddy, orangey flame, that's a little bit cooler than the blue flame, which is the heating flame, which is a lot hotter, okay? So now, looking at this, you can actually see there are 4 different types of stars. There are white dwarfs, which are the smaller ones, okay? We're looking at mass here, so these white dwarfs have smaller masses. You then have the main sequence of stars. Now, our sun is one of these ones in here. Its temperature is around about 8,000 degrees Kelvin. Okay, its luminosity is just over 1. It's around about here. So this is our sun. One of these ones. Just a main sequence star. It's a mid-range star. It's a mid-sized star. Nothing particularly special about it. It's right in the middle of everything, actually. And these... You can see these main sequence stars follow a certain pattern. And this certain pattern basically means the hotter they get, the brighter they are. Okay? You then have these 2 sets over here, which are called giants and supergiants. And this basically relates to the size of the star again. Okay? And they have more mass than the main sequence stars. Okay, let's have a look at this idea of magnitude, apparent magnitude versus absolute magnitude. The first thing I want to look at are these numbers down here. Okay, these numbers indicate the brightness, the magnitude, how bright the sun is, or the star is. What you'll notice is that the brightest star that we can see is obviously our sun. That's the closest one to us. And its apparent magnitude is minus 27. Well, the brighter the star, the larger negative number it has. Okay? The duller the star, the larger positive number it has. So we've got to remember that a negative 27, although it's a low number, it's actually much higher magnitude. And positive 0.9, although it's a higher number, it's actually a lower magnitude. So it's a lot duller. Okay, so let's have a look at some of these stars down here and constellations. This is the constellation which you should all know, the Southern Cross, and this star is in the Southern Cross. Orion, you may have heard of Orion's belt, 3 large stars in a row. Okay, that's 2 of them, Rigel and Betelgeuse. And this star right here, Alpha Centauri, is the closest star to us. Now, it has an apparent magnitude of minus 0.33. So that means it's relatively bright. It's brighter than the rest of these ones as far as we can see. But, interesting thing, if we look across this side, this is our absolute magnitude. So if we were to line these up in order of brightest to dullest, we're looking for the largest negative number. So this would be number 1 right here. This would be the brightest star, followed by these 2 at the same time, then by this one up here, then down to this one, then the Taurus, and then we have the Alpha Centauri. So if we have a look at these ones, Sirius, which is, according to us, the second brightest star that we can see after the Sun, is actually one of the dullest stars in this list. So this is what we mean by apparent magnitude and absolute magnitude. It looks brighter because it's closer. Okay? Same as Alpha Centauri. Alpha Centauri is the closest star to us, so it's the 4th brightest one that we can see, but overall, its brightness is actually only 4.7. So its brightness isn't very bright in comparison to some of the other ones. Okay? If you look down here, this Beta Centauri is a lot brighter at minus 5. It just doesn't look as bright because it's further away. Okay? So that's what absolute magnitude and and apparent magnitude are. Okay, you can see over here. The absolute magnitude is the measure of how much light the object actually emits. Okay, whereas the apparent magnitude is a measure of the scale, how bright the star appears as viewed from Earth. Let's have a look at the life cycle of stars. What can actually happen to a star? Well, going back to our original map, I'll just go back a little bit here. We saw there were 4 different types of stars. Okay, remember we got the large giants, the main sequence, and then the smaller dwarfs. So, those smaller dwarfs, what happens to them? When they burn out, they become a white dwarf, and then they become a black dwarf. Okay? The mainstream star, which is our sun, when it burns out, it will become a red giant. Now, what can happen from here is that it might just, if it's one on the smaller side, it might turn into a white dwarf straight away. However, what might happen, if it's big enough and if there's enough heat, all the hydrogen that is turned to helium, the helium will now burn, and it will become a red giant. Those giants, those large stars that we see, when they burn out, they'll burn all their hydrogen, and then they'll burn all their helium. And then what happens is they actually get more. They get carbon, which is burnt in the core. And they also have iron as well. Okay? We said there are larger elements. The longer that a star is around, the more fusion there is, the more elements that are created. Now, this is probably some of the stuff that you may have heard of, supernova. So a supernova is formed by a large star basically dying and running out. Once you have a supernova, which is the implosion of the star, it can go to a white dwarf or a black dwarf, just like the other ones. It can go into what's called a neutron star, and one which you've heard of before probably, it can turn into a black hole. So a black hole is created by a large star burning out or dying. Okay? Question for you. Could our sun create a black hole? I'll leave that one with you. So, have some types of stars been around longer than others? Well, yeah, if you think about it. Next time you look up to the starry sky at the night, take a look around and have a look at all the stars. Probably it won't look as bright as this, but have a look at the stars. When you look at them, I want you to think back to a picture of a forest. Because if you think about a forest, not all of these plants in here are the same type. Some of them are large, some of them are small. Some of them are younger, some of them are older. And that's exactly the same as when you look up into the starry night. Okay? They have various stages of growth. Then they are all on different stages of their life cycle. Okay? So, it's what you've got to think about. When you look at the stars, they're not all the same. They're not all in the same point in their life cycle. They are different. So, hopefully by the end of this lecture, what I wanted you to be able to do is name some of the ways that stars can be different. Remember thinking about, we have a look at temperature, we had a look at mass, we had a look at the brightness. Remember there was apparent and there was absolute magnitude. We also had a slight look at the colour as well, and the colour related back to the temperature. How does a star release energy? Well, remember we need to think about fusion. Okay, what's going on when fusion occurs? What are the products, and why is it hard to recreate on Earth? And explain how the stars can be different to each other. That just means going into more detail on these ones here. What do we mean by temperature? What is the range for the temperature? What do we mean by mass? And how does that relate to the life cycle of a star? Brightness, you need to explain about apparent magnitude and absolute magnitude. So this is more an in-depth explanation. Thanks very much, guys.